imagine for a second uh, the sheer computational power it takes to train modern artificial intelligence. I mean, we completely take it for granted now, right?
Oh, absolutely. It's just background noise to us now.
Yeah. You point your smartphone at your face and it instantly recognizes you.
Hmm?
Or, you type a complex phrase and a machine translates it into flawless Japanese on the fly.
Right. Or you ask a chatbot to write a sonnet about a toaster and it spits it out in what, 3 seconds?
Exactly. 3 seconds. But behind those split-second miracles is this training process that involves processing billions, sometimes literally trillions, of data points. By all normal mathematical logic, a machine should take billions of years to process all that data and actually, learn anything from it.
It really should. The math is staggering.
But it doesn't take billions of years. It happens in weeks or months. So how's? Today, we are taking a deep dive into a dense, highly technical Wikipedia article on a concept called stochastic gradient descent, or SGD.
Which is quite the mouthful.
It is. But our mission for this deep dive is to decode this exact mathematical engine. We're going to transform what looks like an overwhelming wall of calculus into a really fascinating story of problem solving. Because this single algorithm is basically the beating heart that makes all of modern machine learning possible.
Okay, let's unpack this, starting with the name itself, stochastic gradient descent. It sounds incredibly intimidating.
It does, yeah. It carries a really heavy academic weight.
Yeah.
But if we break it down, the underlying physical concept is actually very intuitive.
Okay, I'm holding you to that.
I promise. So to understand the stochastic part, which by the way is just a fancy mathematical term for random, we first have to understand the gradient descent part.
Right.
In statistics and machine learning, you are essentially trying to solve a massive minimization problem. You have an objective function, which is often referred to as empirical risk. I want you to imagine a landscape.
Like a physical landscape. Yeah, exactly. A massive, incredibly complex landscape of hills, mountains, and valleys. Your singular goal is to find the absolute lowest point in that entire landscape, because that lowest point represents the minimum possible error for your AI model.
So gradient descent is literally how we find the bottom.
Exactly.
It's like trying to find the very bottom of a valley while completely blindfolded. You can't see the destination. You can only feel the slope of the ground right under your feet.
That is a perfect way to visualize it. Now, in classical batch gradient descent, to figure out which way is down, the algorithm calculates the gradient, the slope, using every single piece of data in your entire training set.
Every single one.
Every single one. It looks at the entirety of the data set to calculate the mathematical average, just to take one single perfect step down the hill.
Which, that makes total sense if you're working with, say, 100 data points in a simple spreadsheet.
Right, it's easy.
But if you're training an AI on, every piece of text on the public internet, evaluating the slope from all those billions of individual pieces of training data just to take one step is completely unfeasible. Batch descent is like surveying every microscopic inch of the mountain before deciding where to put your foot next. It's just computationally crushing.
It is. The computational cost at every iteration becomes astronomical. Your machine would literally never finish training. And this is exactly where the stochastic shortcut comes in.
Okay.
The basic idea actually traces all the way back to the 1950s to something called the Robbins-Monroe algorithm. Instead of looking at all the data to calculate that one perfect slope, stochastic gradient descent samples just a single randomly selected subset of the data.
Really? Just one?
Often, yeah, it's just one single data point. It estimates the entire gradient based solely on that one random sample, and it immediately takes a step.
So SGD is just feeling the ground right under your left toe and immediately stepping down. But wait, I have to push back on that.
Go for it.
If we're just guessing the slope of the entire mountain based on one random single data point, isn't that incredibly risky? Couldn't that one data point be a massive outlier? We could easily step the completely wrong way and start climbing up a different hill.
You've hit on the exact trade-off that makes the algorithm work. You are exchanging a high convergence rate, that perfect, smooth, guaranteed path to the bottom for vastly faster iterations.
Okay, so it's a speed thing.
Exactly.
Yeah.
If you were doing this in a simple three-dimensional valley, yes, you would bounce around wildly and probably get lost. But what we have to remember is that modern machine learning operates in incredibly high-dimensional optimization problems.
Right.
We are talking about models with millions or even billions of dimensions, which the human brain obviously can't even picture. In those high-dimensional spaces, the sheer speed of taking thousands of rapid, slightly imperfect steps drastically outweighs the computational cost of calculating one perfect step.
Oh,
You sweep through the training set, continually shuffling the data to prevent the algorithm from getting stuck in loops, and those noisy, erratic steps will eventually trend downward over time.
so we're basically trading precision for speed and trusting the law of averages to get us there eventually.
That's the core of it, yeah.
But relying on just a single random sample still feels a bit too chaotic to me, especially as data sets get larger. It seems like taking one step forward and 3 steps sideways wouldn't be the most efficient way to learn, even if the steps are really fast.
Well, the field realized that fairly quickly, too. A compromise emerged to bridge the gap between true stochastic gradient descent, which uses just that one single sample, and full batch gradient descent. It's called the mini batch.
Mini batch, okay.
Right. Instead of one sample per step, the algorithm computes the gradient against a small group of training samples at each step. Maybe 32 samples or maybe a few hundred.
Ah, got it. So instead of asking one random person in the valley which way is down, you ask a small group of people to vote. It filters out the absolute craziest answers without requiring you to pull the entire population of the planet.
That group voting analogy captures the math perfectly. And from a historical perspective, this was a massive breakthrough. The sources point out that back in 1997, this was explored under the rather clunky name of the bunch mode backpropagation algorithm.
Wow, bunch mode. Very kitschy.
Yeah, it didn't really stick. But the reason the mini batch became the absolute, unquestioned norm for training neural networks isn't just because the math is smoother. It's because of the physical hardware of computers. Using mini batches allows the code to heavily leverage vectorization libraries.
Ah, I see. So instead of the computer's processor handling one single data point at a time, sequentially, it can process the entire mini batch simultaneously using parallel processing on a modern graphics card. The hardware synergy is the real secret sauce.
That hardware synergy is exactly why it took off. Now, alongside the mini batch, there is another crucial concept you have to manage, and that's the step size. In machine learning, this is called the learning rate, and it's represented mathematically by the Greek letter eta.
Eta, okay.
You have to decide exactly how big a step to take once you know the direction. If you set the learning rate too high, the algorithm diverges. It takes massive, sweeping leaps, overshoots the valley entirely, and mathematically flies off into space.
Right, like jumping across the entire canyon.
Exactly. But if you set it too low, it converges so painfully slowly that you lose the entire speed advantage of the stochastic shortcut.
It's the classic Goldilocks problem. You need the step size to be just right. The source material actually has a really fascinating example of this involving linear regression. It mentions that if you have an over-parameterized case, which just means you have more parameters or variables than you have actual data points, SGD does something deeply unexpected.
The over-parameterized linear regression case is remarkable because it highlights a hidden feature of the algorithm. In that specific scenario, there are technically infinite ways to perfectly fit the data.
Infinite ways.
Right. But even if you keep the learning rate completely constant, stochastic gradient descent will naturally converge to the interpolation solution that has the minimum distance from where it started.
Which means out of all the infinite possible solutions that perfectly solve the problem, it's lazy in the absolute best possible way.
Yes.
It naturally finds the solution that required the shortest journey from its starting point.
Ugh.
But even with a group voting to smooth out the direction and a perfectly tuned step size, I still have a major question about navigating this multi-billion dimension landscape.
Shoot.
What if the valley has weird, shallow grooves? Or what if it's really steep on one side but totally flat on the other? Won't our blindfolded steps still bounce back and forth erratically across the steep walls while barely moving forward along the flat bottom?
That bouncing problem, often called oscillation, severely plagued early optimization efforts. The algorithm would basically waste all its energy ping-ponging across a ravine instead of walking down the center of it. To solve it, computer scientists actually looked outside of mathematics and borrowed a concept straight from physics.
Oh, I know this one. Momentum.
Yes, the momentum method, sometimes called the heavy ball method. The roots of this go back to a 1964 article by Soviet mathematician Boris Polyak. But it was really brought into the mainstream machine learning consciousness around 1986 by researchers Rumelhart, Hinton, and Williams. What's fascinating here is how beautifully the physics analogy maps onto the math.
How so?
Well, we stop thinking about our algorithm as just a dimensionless point making isolated blind steps, and we start mathematically treating it as a physical particle, a heavy iron ball traveling through parameter space.
I get the concept of momentum in the physical world, like a heavy ball rolling down a hill builds up speed, but an algorithm is just numbers in a server somewhere.
Yeah.
How do you give a line of code weight and speed?
By giving it a memory. In classical SGD, every single step is entirely independent of the last one. But with momentum, the next update is a linear combination of the current gradient and the previous update.
Okay, so it remembers where it just was.
Exactly. You introduce an exponential decay factor, usually denoted by the Greek letter alpha, to manage this memory. The gradient, or the slope of the loss function, acts as a force that accelerates the ball. Because the math remembers its past velocity, it tends to keep traveling in the same general direction, which smooths out those erratic ping-pong oscillations you asked about. It literally powers through the shallow grooves.
But wait, if we're mathematically building up speed like a heavy ball rolling down a steep hill, don't we run the risk of completely overshooting the actual minimum at the bottom? I mean, if it's picking up that much speed, it's going to hit the bottom of the valley and just roll right up the other side.
That is exactly where that exponential decay factor alpha comes in. In physics terms, you can think of alpha acting like friction or air resistance.
Ah, friction.
Right. It determines the relative contribution of the earlier gradients to the weight change, slowly bleeding off the stored energy. Without that friction, yes, the ball would oscillate wildly or shoot right out of the valley. But with the right decay factor, the momentum allows it to punch through local, shallow minimums, little potholes on the way down, while the friction ensures it eventually settles smoothly at the true bottom of the valley. It's an incredibly elegant mathematical balancing act.
It is elegant. But looking at how fast AI has evolved, I have to assume even momentum had its limits. The math assumes you're using fixed hyperparameters, meaning you as the programmer have to set a constant learning rate and a constant momentum factor for every single dimension of your problem before you press play.
Right, before you even start.
And as we established, these AI models have millions of dimensions. What if the landscape is incredibly steep in one direction but totally flat in another? Using a single fixed step size for every dimension suddenly seems wildly inefficient.
That realization birthed the adaptive era in the early 2010s. The algorithms needed to get smarter about adjusting themselves on the fly without human intervention. The first major breakthrough was ADAGRAD, or Adaptive Gradient, published in 2011. ADAGRAD is brilliant because it adapts the learning rate on a per-parameter basis.
Meaning different dimensions get totally different step sizes based on what the landscape looks like locally.
Exactly how it works. Imagine our valley is a steep ravine. ADAGRAD looks at the historical sum of your steps. If you've been bouncing wildly up and down the steep walls, meaning those specific parameters are changing a lot and have huge gradients, the algorithm stores that history and throws on the brakes, aggressively dampening the learning rate for those specific dimensions.
Right.
But for sparse parameters, features that don't show up often, like a flat plane where you've barely moved, it boosts the learning rate. So when those rare features do appear, the model puts its foot on the gas and takes a big, meaningful step. This made it incredibly powerful for things like natural language processing and image recognition, where data is often very sparse and uneven.
But ADAGRAD wasn't perfect, right? Because it keeps accumulating all those historical gradients in the denominator of its equation, the math means the learning rate eventually shrinks down to practically zero.
Yeah, that was the fatal flaw.
The brakes basically lock up, and the model just stops learning entirely. Which brings us to arguably the funniest piece of trivia in this entire deep dive. Here's where it gets really interesting. To fix ADAGRAD's lock brakes, two PhD students, James Martins and Ilya Sutskever, invented a method called RMS prop in 2012.
Yes.
RMS prop introduced a forgetting factor, turning that infinite history into a running average so the algorithm wouldn't get bogged down by ancient data. It was highly influential, wildly successful, and it was never actually published in a peer-reviewed academic paper.
It really is an incredible piece of AI lore. It was merely described in an online Coursera video lecture by their professor, the legendary AI researcher Geoffrey Hinton.
I just love that. We have this highly rigorous mathematical field, a field heavily dependent on peer-reviewed validation and exhaustive proofs, and one of its foundational pillars was essentially dropped in an online video lecture.
Just casually mentioned to the class.
Right. Hey everyone, divide the gradient by a running average of its recent magnitude. It works great. And the entire industry just said, yep, sounds good to us. Let's put it in everything.
It speaks volumes to how fast the field was moving at the time. If something worked in practice, Researchers ran with it, proofs be damned, and RMS prop worked brilliantly. But it wasn't the final form. In 2014, we got ADAM, which stands for Adaptive Moment Estimation. Yeah. ADAM is essentially the ultimate hybrid combination of RMS prop's adaptive learning rates and the momentum method we discussed earlier.
Taking the best of both worlds.
The absolute best. It uses running averages with exponential forgetting for both the gradients, which are the first moments, and the squared gradients, which are the second moments. It even introduces a clever bias correction to make sure the mathematical estimates don't lean too heavily towards zero during the very first few training iterations when it doesn't have much history yet.
Wow.
Because of this dual approach, Adam and TensorFlow today, they are dominated by Adam and its later variants, like AdamW or AdamX.
But wait, the source text notes a really quirky detail about Adam. Despite it being the absolute industry standard that basically runs the AI world, its initial mathematical proof of convergence was actually completely flawed.
Yes, it was.
In fact, later analysis proved that there are simple, perfectly smooth, bowl-shaped valleys, what mathematicians call convex objectives, where Adam shouldn't mathematically be able to find the bottom.
Oh.
It can theoretically get stuck. It mathematically shouldn't always work.
And yet, it continues to be used everywhere because of its incredibly strong performance in actual practice. It's a recurring theme in modern machine learning, honestly. Empirical success often massively outpaces theoretical understanding. The engineers build a bridge that carries heavy traffic perfectly, and the mathematicians are left standing on the shore trying to prove why the bridge hasn't collapsed yet.
That bridge analogy perfectly sets up the struggle in the theoretical space. Because while Adam dominates the practical engineering side of AI, the theoretical side, the mathematicians on the shore are still wrestling with the extreme numerical instability of these algorithms and trying to mathematically model how SGD's inherent randomness actually functions in the real world.
Let's examine that instability first, because it's a massive headache. Classical SGD can become wildly unstable if that learning rate, eta, is misspecified by even a tiny amount.
Just a tiny bit off.
Just a fraction. The math becomes unstable, essentially. The feedback loop of the algorithm multiplies on itself, causing our virtual heavy ball to vibrate so violently it shatters the calculation and diverges numerically within just a few iterations. Everything crashes. To solve this, theoreticians explored something called implicit updates, or ISGD.
Okay, so I understand the explicit math calculating the slope and taking a step. How does an implicit update actually stop the calculation from shattering?
In classic SGD, you look at exactly where you are standing right now, decide your slope, and take a leap. It's an explicit equation. If you leap too far, you crash. In implicit SGD, the stochastic gradient is evaluated at the next iterate. The new position mathematically appears on both sides of the equation.
So it's like having a mathematical tether. It calculates the slope based on where you are going to land, pulling you back if that future landing spot is wildly off course. It self-corrects the step before you even fully take it.
That tether concept is spot on. It effectively normalizes the learning rate from the future backward. So even if you wildly misspecified the step size, the procedure remains numerically stable virtually for all possible values of eta. It's incredibly robust.
That's amazing.
But fixing this stability is only half the battle. The sources also dive deep into how mathematicians try to model the actual continuous path the algorithm takes. They try to view SGD as a discretization of a gradient flow ordinary differential equation, or ODE.
Basically trying to draw a smooth, continuous line over all the jagged, random little steps.
Exactly. But an ODE only gets you so far because SGD is inherently, remember, it's just sampling random subsets of data at every step. A standard ordinary differential equation cannot capture the random fluctuations around the mean behavior. So theoreticians have to move to stochastic differential equations, or SDEs.
To capture the randomness. And the source mentions they model this random noise using something called Brownian motion. That's the exact same math used in physics to describe the random jiggling of microscopic pollen particles suspended in water. When I read that, I had to stop.
It sounds totally disconnected, right?
Yeah. I mean, is this just academic flexing, using the math of floating pollen to describe cutting-edge AI? Or does modeling this noise actually help us build better artificial intelligence?
If we connect this to the bigger picture, these theoretical models, the SDEs and the Brownian motion, they are attempts to mathematically tame and map the beautiful chaos of the algorithm to prove exactly why the blindfolded climber makes it to the bottom. And it absolutely helps us build better tools.
Really? How so?
Well, understanding that the noise in SGD behaves like Brownian motion allows researchers to design much better limits, vastly superior learning rate schedules, and even new variations of the algorithm that intentionally inject or manipulate that noise to prevent the AI from getting stuck in a bad local minimum. It bridges the gap between the empirical success we talked about and deep theoretical guarantees.
So what does this all mean? Let's zoom all the way out. We started our journey in 1951 with the Robbins-Monroe algorithm, watched it evolve through the backpropagation breakthroughs of 1986, took a detour through Jeffrey Hinton's Coursera class in 2012, and arrived at the atom optimizer that dominates the frameworks today.
It is a remarkable trajectory, a mathematical framework refined over decades, borrowing from physics, hardware engineering, and pure necessity.
And it's wild to think that every single time you use an AI tool, every time you generate a gorgeous image or ask a chatbot to summarize a document or rely on a medical AI to scan an X-ray, this iterative, stochastic game of blindfolded mountain climbing is what made it possible. A concept that was designed originally for one very simple, pragmatic reason: to save compute time. They just wanted to avoid calculating the whole data set. And that shortcut, that compromise, became the beating heart of modern technology.
Necessity truly is the mother of invention. By embracing the noise and the imperfection rather than fighting it, they unlocked the massive scale we see today.
And that actually leads me with a final lingering thought for you to ponder. Based on that whole section about continuous time and Brownian motion, if SGD's defining feature is its randomness, the stochastic noise it injects, just to save time, is it possible that this noise isn't a bug to be minimized? What if it's the actual feature? Think about it. If the algorithm had infinite compute power and took a mathematically perfect noiseless path every single time, it might rigidly memorize the training data and completely fail at anything new. Could the random, jiggling chaos of Brownian motion be the very thing that forces an AI to be adaptable, to generalize, essentially, to be creative? It makes you look at the errors, the noise, and the random stumbling in your own learning process in a whole new light. Maybe the blindfold is what teaches us how to truly see the mountain.